This is day 24 of coding every day until I hit 1K subs. Today felt like a good day to jump back into some LeetCode problems and see what challenges I could tackle. I ended up solving quite a few, ranging from medium to hard, and even a couple of easy ones. Let's dive into them. First up was LeetCode 1922, Count Good Numbers. Spoiler alert, this one involves combinatorics and large numbers. The goal is to count how many digit strings of length are. A string is good if digits at even indices are even. Lay lower or 2, 4, 6, 8, and digits at odd indices are prime. 2, 3, 5, 7. We also need to return the answer modulo 10 to the power of 9 plus 7, because can be very large. Alright, here's the code. The core idea is that the choice for each position is independent. For even position 0 indexed, there are 5 choices: 0, 2, 4, 6, 8. For odd positions, there are 4 choices: 2, 3, 5, 7. There are n plus 1/2 even positions and n/2 odd positions. So the total count is 5 raised to the power of the count of even positions times 4 raised to the power of the count of odd positions. Since can be huge, we can't just calculate these powers directly. We need modular exponentiation, which is what the quick-mul function does efficiently using the binary exponentiation method. This calculates x to the power of y modulo mod in logarithmic time complexity relative to y. Finally, we multiply the results for even and odd positions and take the modulo again. Next, I tackled a harder one. LeetCode 3272. Find the count of good integers. Spoiler alert, this problem involves palindromes, divisibility, and permutations. We need to find the count of integers with digits. An integer is if it's a palindrome and divisible by. An integer is if its digits can be rearranged to form any k-palindromic integer. A key constraint is no leading zeros before or after rearrangement. So, the approach here is a bit involved. First, we generate all possible n-digit palindromic numbers. We can do this by generating the first half, or slightly more than half if n is odd, and then mirroring it. We check if each generated palindrome is divisible by k. If it is, we've found a k-palindromic integer. The crucial part is that any number whose digits can be rearranged to form this k-palindromic integer is considered. To handle this, we find the canonical representation of the digits by sorting them. E.g. becomes. We store these unique sorted digit strings in a set dictionary. Finally, for each unique sorted digit string in the set, we need to count how many distinct n-digit numbers can be formed using these digits, without leading zeros. This is a permutation with repetitions problem. We calculate the total permutations, men, sex count 0, count all puj, numbers permutations that start with 0. A simpler way, shown here, is to calculate total permutations of the n1 digits after picking a non-zero digit for the first position. We multiply the number of choices for the first digit, n, count 0, by the permutations of the remaining n1 digits, adjusted for repetitions. Summing these counts gives the final answer. Okay, let's switch gears to an easier one. LeetCode 2843, Count Symmetric Integers. Spoiler alert, this is about checking a specific property of numbers within a range. We're given a range, low, high, and need to count how many integers x in this range are. An integer is symmetric if it has an even number of digits, and the sum of the first half of the digits equals the sum of the second half. The code here is pretty straightforward because the constraints are small, up to 10,000. We just iterate through every number a from low to high. The definition only applies to numbers with an even number of digits, so we only need to check 2-digit numbers and 4-digit numbers within the given range. For 2-digit numbers, less than 100, symmetry means the 2 digits are equal. D1 equals D2. This is equivalent to the number being divisible by 11, 22, 99. So we check a %11 equals 0. For 4-digit numbers, between 1000 and 9999, we explicitly calculate the sum of the first 2 digits left and the sum of the last 2 digits right, using integer division and modulo operations. If left equals right, we increment our result counter-res. Numbers with 1 or 3 digits are never symmetric according to the definition. Back to a hard problem. LeetCode 2999. Count the number of powerful integers. Spoiler alert, this one involves range counting with specific digit constraints and a suffix requirement, often hinting at digit DP or a similar counting technique. We need to find the count of integers between start and finish, inclusive. An integer is powerful if each of its digits is less than or equal to a given limit, and it ends with a given suffix string s. Okay, this is the provided code. It uses the standard range counting technique. Calculate the count of powerful integers less than or equal to finish, and subtract the count less than or equal to start. 1. The core logic is in the calculate xs limit function, which counts powerful integers up to x, represented as a string. It first handles edge cases where the length of x is less than or equal to the length of the suffix s. The main part calculates the count based on the prefix of x. The part before the suffix s should start. It seems to use a combinatorial approach. It iterates through the digits of the prefix part of x. For each position I, it calculates how many numbers could be formed if the digit at I was smaller than x, respecting the limit. If x itself is greater than the limit, it adds the counts for all numbers with prefixes matching x up to I1, where the I-th digit is less than or equal to limit, and then stops because no valid number can have x or greater at this position. Finally, if the prefix of x itself is valid, all digits less than equals limit, it checks if the suffix of x is greater than or equal to s. If yes, it adds 1 to the count for the number x itself, or numbers matching x's prefix and having suffix s. It's essentially counting in base limit plus 1 up to the number x, while ensuring the suffix matches s. My previous attempt tried to formulate it as digit dp, which is another common way to solve such problems, but let's stick to explaining the provided combinatorial solution. Finally, an easy one to wrap things up. LeetCode 3375. Minimum operations to make array values equal to k. Spoiler alert. This involves analyzing the effect of a specific operation. We have an array nums and a target value k. We can perform an operation. Select an integer h, such that all current elements in nums are strictly greater than h. Then, for every element nums greater than h, set nums equals h. We want the minimum operations to make all elements equal to k. This solution is quite neat. First, consider the goal. Make all elements equal to k. If any element x in the initial array is already less than k, it's impossible to reach the goal. Why? Because the operation only allows setting elements nums greater than h down to h, we can never increase an element's value. So, if x less than k, we can never make it equal to k. In this case, we return -1. If all elements are greater than or equal to k, we need to bring the ones greater than k down. Consider an element x greater than k. We need at least one operation to reduce its value. The most efficient way to deal with all occurrences of a specific value x greater than k is to perform an operation with h equals x. This will set all nums equals x, and potentially other larger values down to x. However, we want them to eventually become k. The key insight is that each distinct value x that is strictly greater than k requires its own step down. We can think of applying the operation with h equals x for each unique x greater than k. This effectively reduces that value. We don't need to simulate the process. We just need to count how many unique values are strictly greater than k. Each unique value greater than k essentially needs one operation targeted at bringing values down past it, eventually reaching k. So we iterate through the array, check the impossible condition, x less than k, and add all unique values x greater than k to a set street. The size of this set is the minimum number of operations required.